So one of the ways that people sometimes use to understand induction is to have kind of analogies that you can use. And one of the most famous analogies, I think, is the ladder analogy. So here's what we have. I mean, we think of a ladder, and it's got a whole bunch of steps. And what you have is that in order to be able to climb the ladder, you have to be able to get on the very first step, okay? And getting on the very first step is a lot like the base case, right? You know, there's nothing helping you. You just have to, you know, get on the ladder, okay? Now, once you do that, okay, then you want to be able to figure out how to get to the next step, right? And so what you do is you kind of look at a little section of the ladder and you say, hey, if I'm here, then that means that I can get to the next step, right? No matter where I am in the ladder, okay? So if you do that, then you know, that tells you that from the bottom step you can get to the next one, and then you can get to the one after that, and then you can get to the one after that, and so on. And so eventually you'll be able to get to any step, right? So that's the exact idea of mathematical induction. What we have is the base case and the induction step. And as long as you have those two things taken care of, then you're able to go to any rung on the ladder. Now, by the way, if you follow this analogy, you don't actually have to get on the bottom rung to the ladder. You could get, say, it's rung number 10. And then what you've shown is that your theorem holds for any number greater than or equal to 10, right? So, you know, that's occasionally useful. Anyway, let's look at some of the things that can go wrong when you use induction, okay? So these are just failures of the ladder. So the first problem is what happens when you can't get on the bottom rung. So here's my theorem, and it's a ridiculous theorem. N is greater than n plus 1. We all know that's false, okay? But here's how we do the proof. So it's a base case. N is equal to 1. That's obvious, okay? Now, obvious is an important word mathematically because it's used to indicate where the error in the proof is, okay? So if you have a proof, you get to a certain step, you say, well, obviously this follows. Chances are that that's where the mistake is, okay? So right here, when n is equal to 1, this says that 1 is greater than 2. That is false, right? But rather than admit that, we just say obvious and move on, and we'll see what happens, okay? Now here's the induction step. We have to prove that P of n implies P of n plus 1, okay? So let's do it. We assume that P of n is true. That means that n greater than n plus 1 is true, okay? And now we add 1 to both sides. So we have n plus 1 is greater than n plus 1 plus 1, which is just n plus 2. So yes, assuming that P of n is true, we get that P of n plus 1 is true. What went wrong? Again, it's just the fact that we were unable to actually prove the base case. We just pretended we did. Okay, that's one of the things that can go wrong. Here's something that can go wrong. What's happening here is that we actually can't get from one rung to the next. So here's the theorem that we're doing. We're saying that all horses are of the same color. So there's no horse of a different color, okay? And we're going to prove it by mathematical induction. And we're going to be a little bit more formal. What we're going to talk about is sets of horses, okay? And what we'll say is that if you have a set of horses, right, then all of the horses in that set must be of the same color, okay? And we'll use induction, and we're using it on the size of the set, okay? It's actually something interesting, something new that we haven't done before. We've been doing induction over integers. We're actually still doing induction over integers. It's just that really what it looks like we're doing is doing induction on sets, right? But we're really doing induction on the size of those sets, and those are integers and non-negative integers, okay? Anyway, base case n equals 1, obvious, right? You should be attuned to that word by now. But actually in this case, it really is true. Because if I have a set that has only one horse, then it is in fact true that all the horses in that set are of the same color, right? You know, there's only one color, okay? So let's look at the induction step a little carefully, okay? So in the induction step, what we say is, well, P of n implies P of n plus 1. And here's what we're doing. We're going to assume that P of n is true, okay? And we're going to show that it's true for n plus 1. So in this little picture, n is equal to 4, okay? And what I have is a set here of 4 horses. And here's another set of 4 horses, okay? So what I'm saying is that each one of those sets, right, all of the horses are the same color. There's some kind of an orangey color there. Now, what we'll do next is we'll kind of take a look at the intersection of those two sets. Okay, and here it is. And if you look at the intersection, well, they're all of the same color. And so right here, this guy is of the same color as the intersection because it's of the same color as this set, right? And this guy has to be of the same color here, right? And so what we have is that since the sets in the intersection are of the same color, then these two horses that were kind of outside of it also have to be of the same color, right? It's kind of a nice little argument, right? Which is that, hey, I got two sets, each one of those is of the same color, right? And because of the way that I constructed them, they have something in common, right? Because I started with a set of 5 horses and I broke it into 2 sets of 4 horses. There's some overlap, right? And because of the overlap, then that means that all of the 5 horses have to be of the same color. Okay, this is actually correct. Okay, it's correct when n is equal to 4. Okay, it's correct when n is equal to 5. It's correct when n is equal to 3, and so on. But where it falls apart, okay, is when you have only n is equal to 1. Okay, because at that point, here we have our horses, right? There's 2 horses. And when I break it up into 2 sets, right, I get all but the second horse, okay? And then I'll look at everything except the last horse, okay? So these are my 2 sets. Each one of those is of the same color by induction, not a problem there. But now there is no horse that actually is on both sets. And so now I can argue that the first horse and the last horse must also be of that, quote, same color. So sorry, that's where it falls apart. This picture is very nice. It's very misleading because the picture seems to indicate that the argument works, right? You know, if I look at a set, then I just ignore the first element of the set. I find a nice subset. Ignore the last element, I get another subset. Both of those subsets are smaller by induction. Each one of those subsets has horses only of the same color. Look at the intersection. There's some horse in common. Voila, all of the horses are of the same color. Not so fast, right? You know, the intersection could actually be empty. So that's another thing that can go wrong. Okay. Here's another example of kind of not being able to get on the next wrong. And that is saying that all natural numbers are small. Okay. So base case, n is equal to 0. Obvious. And in this case, I'm actually going to take it again. This is really an obvious statement. We're saying that 0 is small. Well, come on, you know, what could be smaller than 0? So yeah, I think that's true. 0 is small. So now we look at P of n implies P of n plus 1. So we assume that n is small. Okay. Well, if n is small, n plus 1 is just a little bit more than n, right? It's just 1 more. So n is small, that means n plus 1 has to be small. Voila, P of n implies P of n plus 1. What exactly went wrong here? Well, what's going wrong is that we never really were precise on what we mean by small, right? So is it really true that P of n implies P of n plus 1? Maybe 1 is small, but 2 isn't, right? And that's just the difference of 1. I mean, we doubled in size. We're just not very careful with what we mean by small, and that kind of has a slippery slope type feeling to it. So that's what's wrong with that, right? So that's why we can't quite make this argument, right? By the way, you might try a related proof, which is that every integer is or every natural number is interesting. Okay. Now here's kind of an important point, and that is that there has to be a finite number of steps, otherwise the proof doesn't work. Okay. So here's what happens when you have an infinite number of rungs in the middle. Okay. So this is okay. Here's the beginning, right? And there's a rung, and then we have an infinite number of rungs all the way out, you know, to infinity, so to speak. So this is fine. This is what's not right. This is where you get on, and then you have an infinite number of rungs, but then the ladder picks up again. And the problem is that you can get from here to here, and from here to here, and from here to here, and so on, right? But you never actually get there, right? And the reason you don't is because you have an infinite number of rungs before you get to this kind of second infinite ladder, okay? So that's what can go wrong. So here's an example of that. We'll look at Achilles, who's a very fast Greek. and a tortoise, and they're having some kind of a foot race. Now Achilles is very, very fast, and so he's gracious, and he gives the tortoise a 100-meter head start. He says, yeah, you go ahead. Tortoise says, fine, and starts running, 100 meters ahead. Now the tortoise runs at a constant speed, and so does Achilles, right? And you would think, right, just from common experience, that Achilles will overtake the tortoise very quickly, but in fact, that's not true. Achilles can never overtake the tortoise, and this is why. We'll use mathematical induction. So I'm going to separate the time steps like this. T1 is the time when Achilles finishes running 100 steps, 100 meters. Okay, that's actually where the tortoise starts, right? So here's what happens. At T0, Achilles is over here, and the tortoise is over here. Now at T1, Achilles makes it here. Okay, right? So that's actually what T1 is. Now the problem is that the tortoise during that time can actually move a little bit, right? So the tortoise actually moves. Now that's okay. Now Achilles has this, keeps running. He's not stopping, and so he gets there at T2. But the tortoise has moved. Maybe not quite that much, but it's moved a little bit, right? So Achilles gets back and says, no, I'm going to catch up with you the next time. So this is T3. But what's the tortoise doing? He's still running. And so on, right? So in general, at any kind of given step, so here's the tortoise, right? That's where the tortoise is at T sub n. Okay? And at that point, Achilles is somewhat behind the turtle, right? It's right here, right? And what will happen is that the tortoise will move to T sub n plus 1, and Achilles will catch up, but only to where the tortoise was at T sub n, right? So it can never keep up because the tortoise is always just a little bit ahead of Achilles, okay? How is that possible, okay? This is actually something that the Greeks worried about and says, there's something we don't understand. The guy who came up with this argument was Zeno, and he made all sorts of similar arguments. He argued, for example, that arrows couldn't actually fly because when you let loose an arrow, then at any given time it wasn't moving. So over a long period of time, it wasn't moving at any period of time. It was just standing there. So it couldn't actually have moved. He even argued that, for example, for the arrow to get from point A to point B, you needed to get halfway there. That took some time. Then to get halfway there again, that took some more time. And then halfway, that took some more time. So you see, he never actually gets to anywhere. He made all sorts of similar arguments. And ultimately, what he was really struggling with was the notion of infinities. And what he didn't understand, and it took us a long time to understand, is that when you add an infinite number of things, you might get infinity, but you might also get a finite number. And we call that convergence, right? And so, for example, in calculus, you will look at series and worry about whether that series, which is an infinite sum, adds up to a finite amount or not. And in this case, in the case of Achilles, actually, yes, that series will converge, and that means that Achilles does get to catch up, right? But if you simply follow this kind of inductive case, then you would say, nope, at none of those time steps does Achilles actually catch up. And by the way, that is true, right? At none of these time steps does Achilles actually catch up. The problem is that those time steps converge to some particular time, let's say 10 seconds, and at 12 seconds, Achilles is ahead, okay? So that's what I mean by having kind of an infinite number of steps in the middle, right? These are all the time steps that Achilles is behind the tortoise, and there's an infinite number of those. But then these are all the time steps that Achilles is ahead, okay? And using induction, we just don't get to these, right? That's what's wrong with that proof.